Perfect. Hello, everyone. My name is Srinivasan, and I'll be talking about one of my recent works with Shashank Agarwal titled Key Value Commitments for Blockchains and Beyond. The primitive we construct is called KVaC, like a duck quack, KVaC. So that's what I'll be talking about today. As I get started, I'd like to talk about I'd like to tell you a brief story on why we're thinking about this problem, and that has to do quite a bit with Ethereum itself, and in particular Ethereum 1.x. So one of the things that's been gaining a lot of importance recently within the Ethereum community, particularly because of state bloat, is the concept of stateless clients. So can we have clients and nodes, maybe many of them, maybe all of them, we don't know yet, that could support this feature of being entirely stateless, where they don't have to store the state, the growing state of Ethereum in order to verify blocks and further add to them potentially. So this is a concept that was introduced way back in even in 2017 and has been gaining a lot of attention since within the past couple of years. And the idea is something like there is an implicit, of course, like ground truth state that is agreed upon by the people who are using Ethereum. But you don't want people to carry around or store this state as much as possible. Traditionally, what would happen is you have this state, and then you would make claims about certain entries in this state, and then people could just verify them because they would have the state in hand. But what if I try to do something else? What if in the effort of going stateless, now what we do is, in addition to claiming things about the state, since the person who's listening to you doesn't actually have the state, you provide them with proofs, right? So you provide them with what's in the state and a proof saying that, you know what, this is actually what is in the state, and even though you don't have the whole state, I can prove to you that what I'm saying is indeed true. So that's the idea behind stateless client, stateless validation, essentially. But how is this going to work, right? So let's actually see how this would translate to in terms of concrete realizations of a stateless client. So the state in Ethereum is organized in the form of some kind of tree or trie. I mean, choose your pronunciation. And of course, it could be severely optimized, right? So it's some kind of tree structure that's optimized in a certain way. But then effectively, if you want to encode this into some sort of serializable fashion, you use something like an RLP encoding, and you end up with essentially a dictionary or a key value map, right? So at this particular address, you have this particular value and so on. This is an encoding. And this is important. I've highlighted key and value because this is going to come back later in the talk. So broadly, you can think of the structure, even though it's organized maybe implicitly as a trie, it's concretely organized as some sort of dictionary, right? And this is the state. This is a huge dictionary that represents the state of Ethereum. And now how would you prove things? Well, going back to the implicit representation of a trie, if you wanted to prove something, let's say, for instance, about the green node right at the bottom right there, you would essentially give the Merkle proofs on the path from that leaf all the way up to the root, right? So that seems simple. I mean, concretely, this would be, you go traverse up the height of the tree, essentially, and you give a bunch of hashes, and then verification is easy. You just do computation of so many hashes, and then you're convinced that this is indeed the value stored at that particular leaf in this trie. But of course, things aren't quite as pretty as how they're shown in this picture. They're quite a bit more ugly, right? There's a lot of, the state is huge, and then you have issues when it comes up to like also having smart contracts and then the state of the smart contracts and so on. So it's actually a pretty big structure. And now if you ask, okay, fine, so let me actually take this monstrosity and ask what is going to be the cost of doing Merkle proofs on something like this, it turns out to be somewhat high, right? So the block proof size in total will, if you look at some sort of estimation of this, seems to be around 1 megabyte, right? Which is pretty big. And if we want to look at a split of how we get these numbers, roughly, if you look at the code bit of it, the smart contract bit of it that goes into it, this is going to be something like 250 to 300 kilobytes. And then the rest of it is somewhat evenly split between regular hashes, right? Hashes for showing non-contract variables, and then roughly about the same for showing stuff about smart contracts, right? So really, apart from that 250 kilobytes, you're spending 750 kilobytes proving hashes, and quite a lot of them. And this is kind of the ground truth. If you think of trying to do full stateless clients, this is going to be the cost if you're working with Merkle trees. So this is a big concern, right? So the size of the block proof being 1 megabyte is quite a lot. Now we could call this down a little bit, and ideas have been explored. Like for instance, you could say, maybe nodes are not entirely stateless. They're somewhat stateless, partly stateful. So you keep around some, say, path, like an idea that has been explored is you keep around, say, past block proofs, right? So you don't get rid of all of them and remain entirely stateless. You keep some state. And then maybe you don't have to send all the proofs every time you want to prove something to somebody. You assume they have some of the proofs already, and then you send the additional ones. The other thing is, of course, to use things like Starks to maybe take all the hashes and make one proof, that all the hashes that would eventually lead to the proof. But again, this could be somewhat difficult. I mean, a lot of work, especially today, a lot of work is going into doing proofs, particularly on Merkle hashes. But yeah, I mean, the KVaC hash that's used in Ethereum is going to be pretty expensive in terms of writing a Stark proof for it. So that's something to keep in mind. It is an avenue that's being explored. But let's look at the other one, because it's a little easier to make progress on. Just look at statelessness as a spectrum, or statefulness as a spectrum, right? So you can be completely stateful, which is what you have today, or you could be completely stateless. Now, if you do something like partially stateful, right? So you store 250 blocks, the past 256 blocks or something like that, then we observe that you could get the proof size drastically down. From 1 megabyte, you fall to something like 200 kilobytes or 175 kilobytes, right? Which is a drastic gain. So this tells us that, well, if you think of statefulness as a spectrum, this is actually viable. And in the other sense it makes sense to think of it is that the more stateful nodes essentially are going to be working with a large state within themselves, and so they have to do a lot of work in terms of I/O, memory, and so on. And of course, bandwidth for communication goes down, though, because you don't have to send these proofs. And of course, if you're more stateless, then you don't have these memory issues, but then you need more bandwidth, because you're going to be transmitting larger proofs. So it seems like statefulness as a spectrum is probably the most practical way we can think about bringing statelessness into Ethereum. And that's sort of my short summary on what's been going on with regards to statelessness in Ethereum, particularly 1.x. And this is actually a somewhat condensed version of many blog posts that have been written in this. So I didn't come up with this name 1x files, by the way. It's too cool for me to come up with. It's actually an existing series of blog posts on that follow the development of statelessness within Ethereum 1.x and the ideas that have been explored. Right, so I would definitely recommend going through them, because they're written really well, and it's truly exploratory in the spirit of research and trying to find out what would be the right way to get this going, right? The summary is that statelessness is here now, and I think one of the things that is mentioned in those blog posts is that even for Ethereum 2, right? So this would probably be an important feature. So statelessness is something that we should be working on right now to get it work and to find viable solutions, because that's going to be important as we go ahead. And that's where our work comes in, key value commitments for blockchains. In particular, this is essentially going to be key value commitments for, say, stateless validation, stateless Ethereum, if you'd like to think about it. So our work is essentially we construct a key value commitment. If you don't know what that is yet, don't worry, I will define it later. But it's a primitive that has very efficient representation. Particular just has two group elements, like two big numbers. Maybe you think about it that way, and has very efficient operations where you can modify the underlying structure very efficiently. You can add stuff to it, take stuff out, modify things inside, and so on. And there is no implicit assumption on how big the structure we're operating with is. So there's independence with regards to the size of the map, and then we can do additive updates oblivious to prior value. Again, this would probably become clear a little more later once we talk about key value commitments. It basically means you can modify this structure pretty easily. Okay, so as a side note, our work, key value commitments, they kind of subsume two other primitives that were introduced before this, which were accumulators and vector commitments, or even subvector commitments. So we get state-of-the-art accumulators and state-of-the-art subvector commitments kind of as a freebie after constructing this key value commitment. So why did we do this? Again, we've talked about it. And now that you have the context, it's for stateless validation of blockchains. And as we recall, statelessness is here and now. This is a problem we should be looking to solve. Okay, but how does this even like fit together, right? So we do know that we're thinking about statelessness, and I'm telling you key value commitments are the way to go. So what is it? And really the power of cryptography, or I guess like any science in general, is the power of abstraction, right? So we're going to think about statelessness via abstraction. Essentially, statelessness is enabled by having state that's compressed yet verifiable, right? So there's some state in the case of Ethereum, it's this maybe this trie, but which eventually gets organized as a key value map or a dictionary, as you recall. And the fact that I can compress it means that I can effectively become stateless, right? But even though it's compressed, it's not losing information completely because I'm able to verify things about this state, right? So that's the idea of having the state being compressed yet verifiable. I'm able to show things about this state, right? And the cryptographic security properties say that, you can't really cheat me, right? So even though I've lost potentially most of the information about the state, you can't trick me into believing things about the state that are untrue. And that comes from the cryptographic security. I mean, if you think about it, Merkle trees or tries are doing precisely this, right? So the whole tree or trie is compressed into one hash at the root, right? So the whole state is compressed into one hash, but by providing hashes from the leaf to the root, you can convince me of elements that are rightfully inside that state. And because of the security of the hash, you can't really convince me of things that are not in the state. So Merkle trees or tries are basically an example of this. But more broadly, we can think of, we want statelessness that is enabled by compressed yet verifiable state, right? And this idea has been around. By changing the underlying data structure, you'll get new primitives, right? So accumulators, which are probably the oldest, and Merkle trees are in some sense an example of accumulators, have an underlying set that gets compressed. Vector commitments have an underlying vector that gets compressed. And in a similar manner, key value commitments are going to be key value maps or dictionaries that get compressed, right? So this data structure matters because you want to think about which data structure you're actually working with. And the reason is you might want to do operations on this underlying data structure, and you pick the right one that lets you do these things, right? So if you want to update things in a particular way, and or you want to add entries, delete entries, or reorganize the structure, maybe, whatever, right? So you have operations that you want to perform on this underlying data structure on the state in Ethereum as we're thinking about the parallels. And those should be supported efficiently, even though now I'm working with a compressed state, right? So that's really the key point. So accumulators, as I mentioned, work really well for situations where the underlying data structure you want to work with is a set. So UTXOs, the UTXO model makes total sense because you have a set of UTXOs, and that's the state. I can compress it, and I can provide proofs of membership, right? So this works really well for that model. But once we come to account-based systems, then you're looking at something that's quite different from a set. Sometimes, and probably even recently, people think about it as maybe like being even a vector, but really the closest approximation is a key value map, right? And as we looked at it before, once you do this encoding and serialize the state, it is essentially a key value map. So this is probably the closest data structure that you want to think about. And then you want key value commitments, which are essentially a way to compress a key value map, right? So you can think of it as account ledger, or essentially the whole state of Ethereum, which is kind of represented as a key value map. And then you could provide proofs with respect to the values corresponding to keys, right? So you could say that, here, you can say that the first entry, the value is V1, right? And I can prove that. I can prove that at key SHA-3 of RLP encoding of that 1 to V1, the value is V1. So that's really what you want to show, right? And then once you show that, you can convince people about what's happening within the state. So let's actually look at a definition of this primitive. Essentially, once you do the initial setup, generate the initial commitment to the empty map, you can add key value entries, right? So you can take a key value pair, k comma v, and then insert it into this existing commitment. What that means is implicitly, if you look at the underlying key value map, a new key value pair has been added, right? And then you can update the value corresponding to keys. And we support additive updates. The reason is we were thinking of maybe not all the way up to smart contracts, but just to begin with, if you're thinking about simply updating balances, making payments, I want to be able to pay somebody, which means I need to be able to decrease my balance by some amount, which is essentially subtractive or additive with a negative sign, and then add the same amount back to someone else's balance. So I want to be able to do this operation, and I want to be able to support that, right? So that's the update operation. Now, the thing is, in each of these processes, especially when you insert elements and so on, in order to prove things, right? So if I want to prove something about my balance, I need a proof. We've talked about in statelessness, you don't have, no one's essentially carrying around the full state. So if you want to prove something to them, you need to provide a proof, right? Saying, my value is 5 and I can prove it to you, right? So there's a proof pi associated with my key that I can show that would convince a verifier that the value is indeed what I claim it is, right? But this proof is going to be, how do you say, somewhat fragile. So if the underlying data structure changes, the proof is going to have to change, and this is an inherent lower bound. This is not something you can get across. It has to do with the fact that the state is now compressed. And you can think of it, this happens in every case, right? Even in Merkle trees, your proof you could change, because if I change the value at some particular leaf, all the hashes from there all to the top are going to change. I mean, the commitment itself will change, and then hashes along the path will change. Now, it depends on where you are with respect to this changed value, on whether your proof would change a little or a lot. But yes, in principle, the proof is going to change. So this is something to do with compression and not to do with Merkle or non-Merkle. If you have compressed representations, this is a cost you're going to have to pay. So that's the operation proof update, is essentially to keep your proof current. If you want to think about it that way, if the state has changed, your proof has to change. And then a verifier can verify the proof against this commitment for a given key value pair and be convinced as to whether that key value pair is exactly what is in the map or not. And what are the things you want? You want correctness, right? So if you do things correctly, proofs are correct, they verify, and so on. And you want key binding. That is, you can produce proofs for keys that don't have any value associated with them, or if they do have a value, you can't prove an incorrect value. So if the value is 5, you can't prove it's 10, right? So that's key binding, and that's, again, the cryptographic security, right? So similar to proving that the value at a leaf in the Merkle tree is something specific, you can't claim another value because of the security of the hash. Similarly, we want key binding that says you can't prove another value against a key. Okay, good. So this is going to work really well for an account-based model, as we've discussed. The question is, do we have solutions for this? And the answer is not quite. Before our work, there were some other issues, and particularly for people who have looked into, can we use RSA type schemes and things like that? These are some of the issues that immediately come up, and I think are on the top of minds for everyone. So the first one is sometimes these constructions have a bit-by-bit efficiency, right? So in other words, if you're thinking about values that are 200 bits, 400 bits, you're going to have a scaling factor of 200 or 400 in terms of how big these commitments or the proofs are going to be, and that's too much. You don't want to deal with that. The second is some implicit bound on the size of the map, and the worst part is sometimes the constructions, their concrete efficiency depends on this bound, right? And that's a strict no-no. I mean, we definitely cannot have efficiency depending on the size of the map. That's not okay. But what about having an a priori bound on the size of the map? Well, sometimes this manifests as larger public parameters, which I guess is also going to be too much depending on how big the structure is. And even if you didn't have that, in a world where the state is growing so quickly, it's probably not going to be reasonable to think of a long-term bound other than something just, exponential or something like that. So it's hard to come up with a conservative bound that makes sense. And then the last thing is the updates require knowledge of prior value, which in the example that I cited, I just want to make a payment. So if I wanted to pay somebody, why would I need to know their balance? I just need to know that I have enough money to pay them. While in earlier constructions, you would have to know what the other person's balance is and only then pay them. So these were the problems with prior constructions. And so our work single-handedly gets rid of all these problems, right? So you have efficient representation, everything is small, no blow up depending on the size of the map, no blow up depending upon the bit length. All operations are efficient in the same way. Everything is constant, and if you remember from the previous slides, it was like 2 or 3 at max. And then we can also handle updates that are oblivious to prior values. If you want to compare against, and I know there are a lot of numbers here, I won't expect you to go through all of them, but particularly maybe of interest is Merkle trees and KVaC. Really, the differences you can see in our work, everything is of constant size, right? So your proofs are of constant size. The time to verify is only a constant number of operations. The time to do changes to this underlying structure also is only a constant number of operations, while in Merkle trees everything is logarithmic. Now the immediate concern here is, though, you have size of h, size of a hash on the Merkle trees, and you have size of group elements or field elements in KVaC. Yes, of course, I don't deny that hashes are much smaller, much easier to compute. While RSA operations, for instance, group operations are going to be a little slower, group elements are larger. I don't deny that. And on a first theoretical front, it is interesting that we can go from logarithmic to constant. But on a practical front, which is probably more important for this audience, we'll come to it. I mean, particularly when you're moving to larger and larger situations, this difference is going to show up, where being logarithmic versus constant does make a difference. And really, the killer application of these so-called public key primitives, right, versus hashes, is that they have additional properties, right? So they have algebraic structure that gets you something else. So for instance, our KVaC commitments are going to be aggregatable. I can take any number of proofs and put them together and give you a single proof. In Merkle trees, this is not going to be possible. There you're at the mercy of how the data is organized in the structure. So you would have to think about whether paths overlap, and only then you can sort of combine proofs. Of course, the other way is to go Starks, like we mentioned earlier. But again, things are getting mature on that front, but it may not get to be as good. And finally, there are the algebraic structure that is offered by public key primitives. While it might seem discouraging that they're slower, they could potentially become faster too. And it is my strong belief that if you put the same effort behind public key primitives that you put into, say, optimizing Starks, you would be able to get these things to run faster as well. And only thing now is you get other properties for free, and that's something to look into. And definitely supporting things like RSA isn't a bad idea in any case, right? So there have been EIPs that look into doing RSA signatures and so on, supporting them to be more efficient. And yeah, that is something that's never going to be a bad idea, in my opinion, right? So that's basically how we compare with other works, and why we claim we get the state of art, even accumulators and subvector commitments. So I'll give a quick sketch of how I'll go through the rest of the talk. Is just mainly going through some aspects of the construction. I won't go into too much technical detail, but just to get a flavor of what the primitive looks like. So we start with what we call an insert-only key value commitment. And while we did this initially just for the ease of and modularity of describing our construction, it seems that there are many applications that only care about inserting things and never changing them. So that's something to think about, because sometimes this construction might be more efficient than the main construction. So like I promised, I'm not going to go into too much of the technical details, but just to show you our insert-only key value commitment to a key value map that has KIVI key value pairs looks like this. And although the expressions and the exponents are kind of scary, they're just two group elements, right? So that's what I would like to tell you. So we're working groups of unknown order, example RSA groups. If you're interested in trustless versus trusted setup, you could work in class groups. You also get better sizes, and you wouldn't need a trusted setup. Yes, ZIs are primes, right? So this is the standard RSA setup. But yeah, as I pointed out, the important thing is it's just two group elements, and that's really what's important. The commitment itself is two group elements. And the way insertion works, you can believe me, and we can come back to this if someone's super interested. But basically, inserting a new key value pair concretely takes 1 hash, 3 exponentiations, or 3 group operations, and then 1 multiplication, and that's it, right? So this is a constant. Doesn't depend on how big the map currently is. Doesn't depend on how big you think it's going to be. And doesn't depend on the bit lengths of these values or anything like that. It's always the same. 1 hash, 3 exponentiations, 1 multiplication. The proof is going to look also exactly like a commitment. In fact, it's the commitment to every key value pair apart from the one you're trying to prove, right? So this is just some context. This is usually the case in many of the constructions, and it gives you a few properties for free. When you insert a value, the old commitment is your new proof. And then when you want to update your proof, you just do insertions. And as we saw, insertion is super efficient, right? So proof updating is super efficient. Verification is also an insertion, which again is going to be efficient. So in one shot, just by the fact that insertion is efficient and the structure of our commitment, every operation we're thinking about is efficient. And that's basically the insert-only construction. Security is based on RSA, the RSA assumption. I'm not going to go into why it's secure, but you can take my word for it that it is secure under the RSA assumption. The increment-only commitment is a commitment that assumes essentially that you have all keys with value 0, and then you can increase the value at a particular key by something fixed. Let's say here 1. You could do arbitrary, doesn't really matter, but for us it suffices to think about incrementing by just 1. You can see again, we're working in a group of unknown order. Now you only need one group element, right? So it's even simpler. And as we go on, we will actually see that this entry mimics the second entry in the insert only. But yeah, for now, it's a single group element. Incrementing is super easy. It's basically just one exponentiation after computing a hash. And the proof, though, becomes a little more complicated. And this is why we need field elements. Basically, you can think of it as the proof has two components that talk about the exact value. So if I'm trying to prove that the value within this as a particular key is, say, 5, right? So the way this thing is constructed, you can, in principle, if I don't add additional pi2 and pi3, if I try to go the same way as I did for insert, you can make false proofs that the value was 4 at one time, 3 at one time, 2 at one time, and so on. And if you don't want this to happen, you have to provide what's called a non-membership proof. So I'm proving to you that there are 5, and I'm also, in some sense, proving to you that there aren't 6, right? So now you can't prove 4 because you can't prove 4 and not 5 because there are 5. So that's basically why these two elements come in, and they're basically going to be something like field elements. They're doing primality, like coprimality checking in the exponent. That's a rough idea of what's going on there. But even though we've added these elements, remember, like, field elements are going to be like fixed length. Like even if we're thinking about 128 bits, that's like totally fine. And the proof updates are still, they need more than just one exponentiation, but it's just you add one more multiplication and do some modular arithmetic over these field elements. So that's not much at all. Verification is also similar in terms of its cost. So that's the increment only key value commitment. And why did we construct this increment only? That will be clear in our final construction, which is KVaC. Basically, if you look at KVaC, and if you stare at the exponent of the first component, you can see that it's linear in the VIs. And remember, I want to support linear updates to VI, right? I want to be able to add delta to VI if I wanted to. And you would think that, oh, well, because it's essentially a linear function, you can do this, right? So you can just essentially take the coefficient of VI in that linear expansion, G to that thing, and then raise that to delta. And then if you multiply, you're good. You would actually update it. Except that the computing that term where the exponent is essentially the coefficient of VI is going to be expensive, because if you see, those coefficients are big products of z's, right? So now computation would start depending on n. So that becomes a problem. So in order to avoid this, we're going to take what seems like a really silly route, like even a cop-out, but let's go with the flow, right? So what we're saying, suppose when we want to do an update, we essentially pretend that, there wasn't a value to begin with, and we just insert, right? So in some sense, 5 is already stored at a particular key. I want to change it. I want to add 3 to it, but I'm just going to pretend 5 isn't there because I don't know anything about it and I don't need to know anything about it. I'm just going to say I'm going to insert 3 at the same spot and then see what happens. And turns out this is actually a very good idea. It changes the form of the commitment a little bit, but it does do the job. If I insert oblivious to what was there before, it does update the value at the corresponding key. So you can see that V1 changed to V1 plus delta, even though I added an extra Z1, and that's fine, but the value changed correctly. I'm still able to track, the values corresponding to different keys very clearly. And you can see that I can keep doing this. I can do the insert as before, and then I can continue inserting things as before. If you insert at values that have already been inserted, you're essentially doing updates. And that's the semantic change. But you don't need to be worried about whether someone has inserted there before or not. You don't need to know what the value is. You just go ahead and insert, oblivious to what's happening. And if there was a value, it gets updated. The other way to think about it is you can pretend that the values at the keys were 0. And then as you do these updates, you're changing the value corresponding to keys. So this does, as I said, change the form of the commitment, but in a very cute way. So you can see the second component essentially starts tracking the number of updates. So every time you do an insert, you are effectively updating that location. And the second component keeps track of how many updates you have made. Now you can see where the increment-only commitment is going to come in. Essentially, every time you do an insert or an update, what you're doing is you're increasing the number of updates by 1. Right, and the second component is a commitment to how many updates have been made in each of those spots, right? So this is essentially our full construction, and it continues having only 2 group elements. And in terms of how would you prove things, well, we can do that again by abstracting this out and looking at it. The first component is basically an insert-only key value commitment, and the second component is an increment-only key value commitment. Put them together, you get KVaC, which is a full-blown key value commitment. It's so clean. It's almost like everything got wrapped into a nice tiny present with a bow, right? And so how would you prove things about this commitment? Well, we already separated out saying there's an insert-only key value commitment and an increment-only key value commitment. So you give proofs for both, and then you're done. So remember that we already knew how to prove things for insert-only key value commitments as well as increment-only key value commitments. You kind of combine them together, and that gives you the proof for KVaC. How do you update these proofs? Well, update the independent parts, right? And we already know how to do that. And the part to recall is that each of these were efficient in terms of representation and execution, which means KVaC as a whole is also going to be completely efficient in terms of all the operations. Okay, so that's essentially the summary of the work. We get a key value commitment KVaC that's efficient in terms of representation operations. You don't need, there's no bloat depending on the size of the map, on the bit length of the values that are being used. The whole construction is independent, oblivious to the size of the map that is ever going to be committed. And you can perform updates to this map, oblivious to the old values. Just a quick two-liner on aggregation. We can aggregate proofs and batch verify. As of now, only for the full construction. If you've aggregated proofs once, you can't further aggregate them, what we call continued aggregation. So if I have an aggregated proof, can I aggregate something along with that? That's hard. This is a property you might actually desire, because you can imagine maybe proofs being passed along from one miner to the next and so on, and then people might want to add on their proofs, right? So you want to take one proof and then people add their own proofs for transactions they have done and so on. And this is I think an important question, something that we are looking into. It's a hard problem for sure, but I will say that if you don't care about updates, if you're looking at essentially a static data structure where you can only keep inserting new values, we can actually support unbounded aggregation. You can do this thing where you aggregate some proofs together, and then other people come in and add their proofs and aggregate, produce another small proof, and so on. You keep doing it. So this is something that we can do in our insert-only construction. It's just that the increment-only construction, because of this non-membership proof that I talked about, has the problem that you can't aggregate aggregated proofs. But it's something we are looking into. Potentially there's a solution that we can come up with. So that's basically it. So now the question is, I told you so much about KVaC claiming that it's going to do statelessness, and the question is, did it work? Does it actually give you what it wants? Let's actually figure out. Well, we didn't actually go and implement our solution, but we did do what we call a back of the envelope calculation to see how KVaC would fare if you put it to the test. Right, so we're getting some numbers, right? So this is from, I think, somewhat recently, a couple of months ago. We're looking at the number of transactions in a block, trying to see essentially, the block rate and things like that. And so if you want to do high-level back of the envelope calculation, if I assume something like 200 transactions per block and run the calculation, our block proof size, if you used KVaC instead of Merkle hashes, is going to be 400 kilobytes as opposed to the 1 megabyte, right? So you're saving quite a bit. And this is what I told you right at the beginning, is I promise you that as you get bigger and bigger, the fact that you have logarithmic versus constant is going to matter. And the fact that you have properties like aggregating proofs, that's really what's happening. If you look at the proof size here that we've estimated of like 0.8 kilobytes, that's because you can actually combine proofs. And if you recall from Merkle trees, that wasn't possible, right? So even though these group elements are bigger, you gain quite a bit on the proof size. So we can do 400 kilobytes as opposed to 1 megabyte. And now, if you're asking, what about the 175 kilobytes? Well, you can do that here too. If you can think of statelessness or statefulness as a spectrum, and again, do the same calculation, and you would win again, because we're going to get the same benefits of not sending around all the proofs and just storing things, right? I will say, though, that particularly if you want to look at the cost of operations in terms of time, and maybe thinking of other benefits that Merkle trees do provide in terms of hashes being small and fast, Merkleizing this data structure in some way, KVaC in some way, would also be very beneficial. And for instance, people are looking into Merkle tries and things like that right now, where you're combining in some way essentially vector commitments and Merkle trees, right? So you could do the same. Instead of looking at vector commitments, particularly if you think that key value commitments are more suited to this data structure, you could Merkleize key value commitments, right? And come up with a Quirkle try, I don't know, something like that. And the thing to be noted is that something like that is probably the way to go. The reason is the reason Merkle trees win so much is not just because of their size and their efficiency. It's that by giving up on the asymptotics, right? By giving up on wanting to do constant size proofs and say we're going to do logarithmic size proofs, there's some amortization that can happen in terms of updating many proofs at once. For instance, can I sit and can I look at all the Merkle proofs and update them at once? Merkle trees kind of win there because of the fact that the proofs are longer. It means that updating all the proofs at once is actually a little easier. While if I compress the state way down and the proofs way down, you kind of have to change all the proofs, and this isn't something you can get out of. So if you want to get all these properties together, right, the size and time benefits of Merkle trees, these updating multiple proofs at once, amortization benefits of Merkle trees, the fact that you get many interesting properties like oblivious updates, aggregating proofs and things like that, the properties that public key primitives offer you, yeah, I think the way to go would be to look at some sort of combination of these two primitives, and that will be probably the best of all worlds that we can think of. So the moral of the story is, hashes are great if you don't have way too many of them. And today's boat means we might have to jump ship, right? You might have to change boat and go start including some public key crypto, which is never going to be a bad idea. And I guess bottom line is we won't know if we don't try. So I think there are a lot of things in place to explore this option. And so I think it's a good idea to try it. Again, final thoughts, statelessness is here and now. We have to think about solutions for this. KVaC could be a way to do it, at least a part of the puzzle that could help with this, right? So we construct this key value commitment with everything being efficient that gives you state-of-the-art accumulators and subvector commitments even, right? So it gives you the best of all these primitives. And that's all I had to say for today. I'll stop and take any questions. Thanks, everyone. Okay. Sure. Thank you. Yeah. You too. Thank you.